Picture this. You are a middle school teacher, and you have just asked your class what they think was the greatest invention in human history. The answers come in predictably. The internet, the smartphone, electricity, the printing press, fire. Someone in the back says pizza, which you write on the board anyway because it's Friday and you've stopped fighting certain battles. And then one kid, there's always one kid, says the wheel. And the class groans because the wheel is the obvious answer, the boring answer, the answer that adults have been giving since forever, the answer that appears on motivational posters next to phrases about reinventing things. The wheel has become so culturally embedded as the symbol of obvious invention that it has lost all its actual interestingness. People treat it like it was inevitable, like some early human just looked at a round rock one afternoon and thought, transportation, and that was that. Here is what actually happened. The wheel was not obvious. The wheel took thousands of years longer than almost every other major human technology to be invented. Humans had agriculture, cities, writing, metallurgy, ocean navigation, and monumental architecture before anyone put a wheel on an axle and used it to move something. The wheel is younger than the pyramid. It is younger than cuneiform writing. It is younger than bronze tools and domesticated horses and irrigated fields. The wheel, the technology that modern people treat as the baseline symbol of basic cleverness, was one of the last fundamental technologies that ancient humans figured out. And the story of how they finally did is considerably stranger, more complicated, and more revealing about the nature of human innovation than anyone who groans at the obvious answer has ever been told. Start with the problem the wheel was invented to solve, because without the problem, the solution makes no sense. Moving things is hard. This is a truth so foundational to human experience that it barely registers as a statement. But in the ancient world, the difficulty of moving things, particularly heavy things, over distances, was one of the primary constraints on economic and social organization. Agricultural surplus was only valuable if it could be moved from where it was produced to where it was needed. Building materials for monumental construction were only useful if they could be transported to the building site. Trade goods were only tradable if they could actually get from one place to another. Ancient humans solved the movement problem in several ways before the wheel. The most basic was carrying human backs, human arms, human heads used as transport platforms across cultures worldwide. Domesticated animals extended carrying capacity enormously. Donkeys, camels, horses, and oxen could carry loads that no human could manage, and domestication of these species predates the wheel by centuries or millennia in most cases. Sledges, flat platforms dragged across the ground, allowed heavier loads to be moved by animals or human teams, and sledge use appears in the archaeological record well before wheeled vehicles. Rollers are the technology most commonly cited as the conceptual ancestor of the wheel, and they appear in ancient construction contexts across multiple cultures. A heavy object placed on rounded logs rolls more easily than one dragged on flat ground, because the rolling contact replaces sliding friction with rolling friction, a substantially lower resistive force. Moving heavy stone blocks at construction sites using log rollers is a technology that various ancient cultures appear to have used, and it introduces the key observation that round objects in contact with the ground reduce resistance to movement. But here is the critical point that the rollers led to wheels narrative usually glosses over. The conceptual gap between a roller and a wheel on axle is enormous. A roller is a passive object placed under a load. A wheel on axle is a rotating element attached to a vehicle in a way that the rotation is continuous, controlled, and coupled to forward motion. The mechanical difference between these two systems requires a conceptual leap that, historically, took millennia to make, even with the roller right there as an observable intermediate step. The oldest confirmed wheeled vehicle in the archaeological record dates to approximately 3,500 BCE in the region of the Black Sea and Caspian Sea. Specifically, the cultures of the Pontic-Caspian steppe and the nearby areas of the ancient Near East, including early Mesopotamia. The evidence comes from multiple sources that converge on the same time window. Physical remains of wheels and axles in archaeological deposits, depictions of wheeled vehicles in early pictographic writing and art, and the presence of wheel ruts at ancient sites. The wagons depicted in early Mesopotamian pictographs and the wheels found in burial contexts from the Pontic steppe region share a fundamental design: solid wheels made from planks of wood joined together, rotating on a fixed axle. These are not wheels in the most elegant sense. They are heavy, clunky, requiring significant draft animal power to move. But they work. They reduce the friction of moving heavy loads across flat terrain sufficiently to represent a meaningful improvement over sledges and pack animals for bulk cargo transport. The solid plank wheel is the first wheel, and it is worth sitting with how far it is from the thing you're picturing when you hear the word wheel. It is not a spoked circle of elegant economy. It is essentially a slice of tree trunk, or a composite of planks, thick and heavy, with a hole through the center for the axle. It has none of the lightness or structural efficiency of later wheel designs. It works because round things rolling on the ground reduce friction. But it works in the most labor-intensive, material-wasteful way possible, and it required enormous animal power to be practical. The development of this design, heavy, solid, functional, and not the more elegant later versions that most people visualize, is itself revealing about how ancient technological development worked. Ancient inventors didn't design optimal solutions from first principles. They developed functional solutions from available materials, existing craft knowledge, and incremental observation. The first wheel was the wheel that could be made with the materials and skills available, not the wheel that would be ideal in some engineering sense. The materials and craft knowledge required for wheel and axle construction were not trivially available, and understanding the prerequisites helps explain why the wheel appeared when and where it did rather than earlier or elsewhere. Wood is the primary material of the first wheels, and working wood into the precise shapes required for a functional wheel axle system requires carpentry skills of considerable sophistication. The hole through the center of the wheel through which the axle passes must be sized to create a close enough fit with the axle that the wheel doesn't wobble excessively during rotation, while leaving enough clearance that the wheel can rotate freely without binding. This fit tolerance is not trivial to achieve with stone and copper tools. The woodworking required for early wheel construction was among the most demanding craftwork of its era. The axle itself presents additional engineering challenges. The axle must be strong enough to support the weight of the load without breaking, smooth enough in its bearing surface to allow the wheel to rotate with tolerable friction, and precisely cylindrical over the portion that contacts the wheel bearing. Producing a cylindrical wooden shaft with consistent diameter over its length requires lathe-like rotation during cutting or sophisticated hand tool skills that produce equivalent results. The archaeological evidence for early wheel technology includes evidence of advanced woodworking capability, tools, techniques, and craft traditions that represented decades or centuries of development before the wheel itself appeared. Bronze and later iron fittings played an increasingly important role in wheel technology as metallurgy developed. Wooden axles and wheel hubs wear rapidly under load, and the wear increases friction over time until the vehicle becomes unusable. Metal bearings and hub liners, bronze or iron components that protected the wooden contact surfaces, dramatically extended the service life of wheels and reduced operating friction. The progressive integration of metal components into wheel technology is part of why wheeled vehicles became substantially more practical and widespread during the Bronze Age than they were in the earliest period of wheel use. The spoked wheel is the innovation that transformed wheeled vehicles from heavy, slow, draft animal-intensive cargo movers into fast, maneuverable, militarily significant machines. And its development represents one of the most important advances in ancient engineering. A solid wheel is heavy. The weight of the wheel itself contributes to the total load that the draft animal must move, and for small loads, the wheel's own mass becomes a significant fraction of the total transported mass. This limits the efficiency of solid-wheeled vehicles for light, fast transport. The wheel is just too heavy to accelerate and maintain speed without enormous power input. A spoked wheel, a circular rim connected to a central hub by thin radial spokes, achieves approximately the same structural function as a solid wheel while removing almost all the interior material that contributes only dead weight. A well-designed spoked wheel is dramatically lighter than a solid wheel of equivalent size, and the reduction in wheel mass allows for faster acceleration, higher speeds, and smaller draft animals to move comparable loads. The spoked wheel appears in the archaeological record approximately 2000 BCE, roughly 1,500 years after the solid wheel, and its immediate impact on ancient military technology was transformative. The light chariot, a two-wheeled vehicle built around spoked wheels pulled by horses, became the dominant military technology of the ancient Near East, the Aegean, Egypt, China, and India within a few centuries of the spoked wheel's development. The speed and maneuverability that spoked wheels enabled made chariot forces the decisive military arm of the Late Bronze Age in ways that solid-wheeled carts had never been able to achieve. By the way, if you want to go even deeper into the secret lives of ancient humans, I just launched a full course called The Secret Lives of Ancient Humans. 10 modules, 3+ hours of content covering everything we never talk about on YouTube. What they feared, how they communicated, what hunted them, and much more. Plus an exclusive PDF guide included. Link in the description. See you inside. The engineering of a spoked wheel is considerably more demanding than the engineering of a solid plank wheel. Each spoke must be shaped, fitted, and secured in a way that distributes load evenly around the hub and rim without any single spoke carrying excessive stress. The rim must be curved into a circle and joined at its ends in a joint strong enough to maintain the circular form under load. Early spoked wheels used wooden components for all elements, with the design of the spoke tenon joints and rim segments requiring precision woodworking well beyond what the first solid wheels demanded. The development of the bentwood rim, producing the circular rim by bending thin wood strips around forms and securing the bent shape through joinery and binding, represented a manufacturing innovation that made consistent, efficient rim production possible. The use of heated water or steam to soften wood for bending was known to ancient woodworkers in various contexts and was almost certainly applied to rim production, though the direct evidence for this is indirect. The geographical question, why did the wheel appear where it did and not elsewhere, is one of the most discussed puzzles in the history of technology, and the answer illuminates something important about the relationship between technology and environment. The Fertile Crescent and the adjacent Pontic-Caspian steppe were among the first regions to develop wheeled vehicles, and these regions share a set of environmental characteristics that favored wheel development. Relatively flat terrain, open landscapes without dense forest cover, domesticated draft animals available in sufficient size and number to make wheeled vehicles practical, and social and economic complexity that created demand for bulk cargo transport. Flat terrain is more critical to wheel utility than it initially appears. A wheeled vehicle is dramatically more efficient than carrying or sledge transport on flat, hard ground. Rolling friction is much lower than sliding friction, but on steep slopes, soft ground, or heavily forested terrain, wheeled vehicles lose much of their advantage and gain significant disadvantages. They can't climb steep grades efficiently, they sink into soft soil, and they can't navigate around obstacles the way a human or pack animal can. Pre-Columbian civilizations in the Americas developed the concept of the wheel. Toy wheels with axles appear in archaeological sites in Mesoamerica, demonstrating that the physical principle was understood, but never applied it to transport vehicles. The standard explanation is environmental. The Americas lacked suitable, large domesticated draft animals and had terrain profiles that made wheeled transport less advantageous than alternatives. Without oxen or horses to pull carts, a wheeled vehicle relies on human power. And human-pulled carts are only advantageous in quite specific terrain and load conditions. Without that draft animal power, the wheel's benefit over human carrying with tumplines and pack frames was limited enough that the technology wasn't worth the investment. This explanation has been questioned and nuanced by various researchers, but the core observation remains. The adoption of new technology is not driven simply by the availability of the technology, but by the cost-benefit calculation in the environment where it might be used. The wheel spread rapidly across the Eurasian steppe and into the Near East, Not because people there were smarter, but because in those environments, with the animals, terrain, and economic organization available, wheeled vehicles provided a compelling advantage. Where those conditions weren't present, the wheel's advantages weren't compelling enough to drive adoption. The potter's wheel adds a dimension to the wheel's invention story that most accounts of the technology ignore. And the relationship between the potter's wheel and the transport wheel is more complicated than the sequential narrative usually implies. The potter's wheel, a rotating turntable that allows clay to be formed by hands while the clay spins, appears in the archaeological record at approximately the same time as the earliest transport wheels, and in some analyses it may predate them slightly. The potter's wheel works on an entirely different mechanical principle than the transport wheel. It is a flywheel, a mass rotating around a vertical axis, used to maintain continuous rotation rather than to reduce rolling friction. The operator spins the wheel with periodic kicks or hand pushes, and the rotational inertia of the wheel's mass maintains the spin between inputs. Whether the potter's wheel and the transport wheel were invented independently, or whether one influenced the development of the other, is a question that archaeologists and historians of technology have debated for decades. The geographic and temporal overlap of their appearances in the ancient Near East has led some researchers to suggest a common origin or mutual influence. Others point to the fundamental mechanical differences between the two applications and argue for independent development. What is clear is that rotating devices for craft production, including not just potter's wheels but also spindle whorls for textile production, predate the transport wheel and demonstrate that the concept of controlled rotation around an axis was available in ancient craft traditions before it was applied to vehicle transport. The mechanical understanding required for a spindle whorl, a weighted disc that maintains rotation to twist fiber into thread, is considerably simpler than the understanding required for a wheeled vehicle, and spindle whorls appear in the archaeological record thousands of years before wheeled vehicles. This suggests that the conceptual barrier to the wheel was not the rotation concept itself, which was familiar from craft applications, but specifically the application of rotation to transport, the engineering insight that a rotating element attached to a vehicle could reduce the friction of movement in a way that was practically useful for cargo transport. The conceptual transfer from spinning pot to rolling cart was not automatic, and the historical record suggests it took a very long time to make. The legacy of the wheel's invention is so deeply embedded in modern civilization that tracing its effects is essentially tracing the entire history of industrial technology. The axle and wheel principle underlies not just carts and chariots, but every rotating machine in the industrial and modern technological repertoire. Gear systems, mills, pulleys, turbines, electric motors, internal combustion engines, gyroscopes, and the drivetrains of every vehicle from bicycles to spacecraft. The transition from draft animal-wheeled vehicles to steam-powered wheeled vehicles in the 19th century was a change of power source. The wheel-axle principle remained. The transition to internal combustion and then electric motors was again a change of power source. The wheel is the persistent element, unchanged in its fundamental mechanical principle from the first solid plank rotation on a wooden axle in 3500 BCE to the carbon fiber wheels spinning on a Formula One car today. This continuity is itself remarkable and speaks to the depth of the mechanical insight embedded in the original invention. The wheel-on-axle is not a technology that was superseded and replaced by something conceptually different. It was a technology that proved robust enough to remain the foundation of rotating machine design across all of subsequent technological development. The social and economic effects of wheeled transport in the ancient world were comparably transformative. The ability to move bulk goods, grain, pottery, metals, stone, by wheeled vehicle rather than human carrying fundamentally changed the economic geography of ancient civilizations. Distances that were impractical for regular trade became routinely traversed. Agricultural surplus could be collected from broader areas to support larger urban populations. Military logistics changed as armies could move supplies in quantities and over distances that were impossible with pack animal and human carrying alone. The chariot's military impact restructured the political landscape of the ancient world. States that could field large numbers of chariots had decisive advantages over those that couldn't, driving both the spread of horse domestication and breeding practices and the accelerated development of military organization and bronze metallurgy to support chariot warfare. The chariot was arguably the first weapon system in the modern sense, a complex technological platform requiring specialized manufacturing, trained operators, organized supply chains, and systematic tactical doctrine. The middle schooler who said wheel was right, and not for the reasons the other kids in the class were groaning about. The wheel is not the obvious invention that modern hindsight makes it appear. It was a difficult invention that came later than almost everything else, required a convergence of prerequisite technologies and favorable environmental conditions, and represented not a single moment of insight but an accumulating process of craft development, observational refinement, and engineering problem solving that played out over centuries. The solid plank wheel gave way to the spoked wheel. The wooden axle gained metal bearings. The chariot wheel was refined into the cart wheel, was refined into the mill. Wheel was refined into the gear, was refined into the turbine and the motor and everything that spins in the service of human civilization. Every step in that chain was made by people applying the same combination of practical intelligence, empirical observation, and incremental refinement that characterized all ancient technological development. None of them were geniuses in the isolated inspiration sense. All of them were participants in cumulative cultural evolution, adding small insights to a growing body of knowledge that eventually transformed a rotating wooden disc into the foundational mechanical principle of industrial civilization. The kid in the back was right to say the wheel. The better question to ask, the question that makes the answer interesting instead of obvious, is how. Now you know.